In this presentation, I'm going to try and clarify a few points on your C1 notes, topic 6, the quantitative or counting atoms. And you'll see that the word that we'll use quite a bit as we go through this is the mole. Now, just before we start, this is at the start of your booklet, and this is really the bits and pieces that C tell us that we should know. And you'll see put in there the relative atomic mass and then the relative formula mass, which we'll move on to. Now, we've done relative atomic mass, so the first page in a bit is really just revision of that from our atomic structure notes. So we'll go over this fairly quickly, and then we'll leave you one example to try. So first of all, a couple of definitions. So the relative atomic mass are because atoms have isotopes, and you remember what isotopes were? Isotopes were atoms of the same element, so where you've got two or more atoms of the same element, and that means they've got the same number of protons, but they differ in mass due to different number of neutrons. Now, because you get a mix of those, and sometimes you'll get more of one isotope than the other, you have to work out an average weight of them. And the average weight is what's called the relative atomic mass. And the strict definition of that is the relative atomic mass of an atom is the average mass of the atom compared to one atom of carbon-12, which is given a mass of 12 exactly. So the whole thing's set on carbon, which is given a mass of 12 exactly. Now, we have to work out an average. So you remember when we did our atomic structure, these were the sort of things that we looked at with atoms. So first of all, we can work out the protons, electrons, neutrons, so use PEN. So there's, for chlorine, 3517. So we'll have 17 protons. So 17 protons with 17 electrons. And then you remember to do the subtraction. 35 minus 17 gives us 18 neutrons. Now, the other isotope of chlorine is heavier. It's got a mass of 37, and the reason for that is it's got more neutrons. So again, atomic number 17, so 17 protons, 17 electrons, and then this time 37 minus 17, 20 neutrons. The relative atomic mass was the average, and you remember that what we found was that about 3/4 for every 4 atoms, 3 of those were chlorine 35, and 1/4 of them were chlorine 37. So 3 atoms of chlorine 35 for every 1 of 37. So to work out the relative atomic mass, RAM, we took the fraction of each isotope, multiplied by the mass number, the fraction of the other isotope, multiplied it by its mass number. So for chlorine, there's the figures there. So 75 over 100, which is basically 75%. The fraction is 75 over 100 multiplied by 35, and then add on the 25 over 100 times 37. Put the figures into a calculator. At this level, keep as many figures as you've got, 26.25 plus 9.25, and then add those together. And in this case, that works out as 35.5. And remember, if you're asked for the relative atomic mass, usually 1 decimal place. There's a couple of other examples, so if you feel happy enough, you can go ahead and do these. Pause the video and then go ahead and do them. If you're less happy, I'll go over the first one, and then you can do the next one. So 12, 6 carbon, 6 protons, 6 electrons, 12 minus 6, 6 neutrons, 13 carbon, 6 protons, 6 electrons, 13 minus 6, 7 neutrons. The relative atomic mass, this has got a very high percentage of the carbon 12, so 98.93. So the relative atomic mass would be given by 98.93 over 100 times 12, and then 1% of carbon 13, so 1.07 over 100 times 13. Put the figures into the calculator, and you end up with 12.0107. And in that case, you probably would round that to 2 decimal places just to show you've got the figure there. So 12.0 or 12.01, depending on what the question asks in an exam question. So you can definitely do the copper one now yourselves. So again, pause it and have a go. I'll go over it again in a second fairly quickly. So 29 protons, 29 electrons, 63 minus 29, 34 neutrons, 29, 29, and then 65 minus 29, 36 neutrons. The relative atomic mass, 69%, so 69 over 100 times 63, plus 31 over 100 times the 65. Put the two figures in, add them together, 63.62, and again, 1 decimal place, 63.6. Now, we're going to use these relative atomic masses to try and count atoms, and you'll see with your periodic table, those figures appear on the periodic table, but in your periodic table, they're just rounded to the nearest whole number. So we sometimes have to work them out, but in your periodic table, the final answer is given to the nearest whole number. Okay, so what's the problem with counting atoms? So what I usually start with is something familiar. So in the chemistry lab, I grab something like a spatula and say, how many atoms do you think there are in a spatula? Now, usually there's a variety of guesses. When we actually show it, there's the number there. About 170,000 million, whatever that number is actually properly called. But it's a huge, huge number. So there's a couple of problems. So what does it first of all tell you about the size of atoms? Well, you've probably said they're very, very small. If you've got that number in a spatula, that means the atoms are very small. And it also gives us another problem, because if we're going to try and count them, the numbers are so big, it takes a long time to count it. So for example, if we were to go 1, 2, 3, 4, 5, and so on, someone's estimated there's the number of years that it takes to count that out. Many, many thousands of millions of years. And basically that's something like 3 or 4 times the lifetime of the universe. It's a huge amount of time. So we're not going to be able to count atoms in the way that we would count, for example, things that we see around us, the number of pens that are sitting on a table or something like that. We can't count atoms in that way. So what we do is we count them in bundles. Now you're familiar with this, because if I was to say to you, how many eggs would there be in 1 dozen? Now you've probably immediately said 12. Or if I said 2 dozen, you would immediately say 24. If I said half a dozen, you'd immediately say 6. Now you're very familiar with those numbers. You probably got 12, 24 and 6 without even having really to think very much about it. And the reason you did that was because you're used to a dozen being 12. For many years you've known a dozen's 12. So if I say 2 dozen, you automatically think of 24. In your head you multiply 12 by 2 and you think of 24. Now we apply the same thing when we look at our study of atoms. And what we have to use is a bigger bundle than that. And that's what the word mole comes in. So the mole is basically, we're going to count in these bundles called 1 mole. Now what 1 mole is they started off with carbon. And what they did was they took exactly 12 grams. Remember in the early definition that everything was compared to carbon 12. So we start off with 12 grams of this. And scientists have counted the number of atoms that are in this. And it's a huge number. And that huge number is what we count in. We count in bundles of this. Now, you're never going to have to use the actual numbers, but what you're going to do is you're going to count in the same way that we'd say 2 dozen, 3 dozen, 4 dozen. You're going to count and you're going to say that there's 1 mole or 2 mole or half a mole or 0.65 mole, things like that. So you're going to count atoms in those numbers. Now, as we said in the introduction, you're used to it. So down here, you'll see, for example, I'd asked a couple of questions. So if you're told there's 1 dozen eggs and 12, you automatically say 24 is 2 dozen. What about this one? A pair of birds. Okay, so you know the idea of a pair of birds, and you automatically think of the number 2. If you had 4 pairs, how many birds would you have seen? Yeah, 8. You'll have 8. The other thing you can use to illustrate this as well is blocks of paper. So you've probably seen around printers and things like that there, blocks of paper sitting. That's called a ream, and in that there are 500 sheets. So if you lift a block of paper, there's 500 sheets in that. So 3 reams of paper, how many sheets would be in that? Again, you probably worked it out in your head. 500 times 3, 1,500. So if you know what the bundle that you're counting in is, you can get the actual numbers. And what we're going to get practice at GCSE is counting in those bundles. So 1 mole of atoms is a huge number. Now we've put it here just to show you what the number is, right? So when you take 12 grams of carbon, what you've got in it is that number there, 600,000. So up that bit there, 600,000 million. Okay, huge, huge number. Now, it's such a big number, we're not used to using it. In maths, if you're used to maths, you can write it as this. It's 6 followed by 23 zeros, so 6 times 10 raised to the power of 23. Don't worry too much if you not use that notation. Just keep in mind there's a big number. And then that's it. We're never going to, at GCSE, use those actual numbers there. What we're going to do is we're going to say that if we've got this number of particles, we're just simply going to call that 1 mole. If we've got twice that number of particles, 2 mole. If we've got half that number of particles, half a mole. So at GCSE level, we're going to determine the actual number of moles. We'll not count this in the actual number of particles. So we'll be talking about 1 mole, half a mole, 2 moles, not the actual numbers of it. And that's just to show you what the number really means. Okay, so how do we do this? Well, the way we do this is we have to find out what 1 mole is. Now remember, carbon is the basis of this. So 12 grams of carbon has 1 mole of atoms present in it. Now, that means that if you take 1 mole of carbon atoms, you'd weigh out 12 grams. So the scientists have used that number from the periodic table. You take the 12 and you weigh out 12 grams. Now, what about magnesium? Well, if I flip up the periodic table, you'll see magnesium over here. All right, so magnesium is there. Now, the number above it is 24. Do you remember over here there's carb, the number of it was 12? But magnesium has 24 above it. Now, what that means is magnesium atoms are heavier. They're twice as heavy as carbon. And what that means is if we want to count out the same number of magnesium atoms as carbon atoms, we have to measure out twice the weight. So 1 mole of magnesium is 24, and that's simply because magnesium atoms are heavier. So 12 grams of carbon would have 1 mole, but 24 grams of magnesium would also have 1 mole, but the magnesium atoms are heavier. Let's take sulfur. So go back to our periodic table. There's sulfur, the number above it's 32. So what we do with it is we weigh out 32 grams of sulfur. So 1 mole of sulfur is 32. So what that means is if you want to get 1 mole of any element, you simply go to the periodic table and you take the number above it. Now, for practice, there's 3 examples there. So could you pause the video, get your periodic table and look up the numbers and see what we should be getting for those. And I'll go over it now in a second. So looking at them, there's lithium, 7, phosphorus, 31, and I've forgotten what the third one was, oxygen. And oxygen is 16. So our answers, 7 grams for 1 mole of lithium, 31 grams for 1 mole of phosphorus, and 16 grams for 1 mole of oxygen. So if we want the mass of 1 mole of element, we simply go to the periodic table. Now, if we were just to use elements, we could only do 100 examples, and that would be it. So we want to use it for various other things. So what about if atoms are joined together? So for example, fluorine, F2. Now we've seen that they're diatomic elements, F2 joined together. So how do we get the mass of 1 mole of it? Well, F, we look up in the periodic table. So go back to our periodic table. There's F there. It's 19. So 19 multiplied by 2 would be 38. So 1 mole of F2 would weigh 38. What about water? Well, water's H2O. Now, what that means is when you've got a molecule of water or a mole of water, you've got 2 hydrogens joined to 1 oxygen. So, hydrogen and oxygen. So again, go back to our periodic table. Hydrogen, which is over here, 1. Its mass is 1. Oxygen we saw a moment or two ago was 16. So what we're going to do for water is we're going to add 1, multiply it by 2 because we have 2 hydrogens. Oxygen 16, add that on. So 1 times 2 plus 16, 18. So if I want 1 mole of water, I'd weigh out 18 grams of it. 16 plus 2, 18 grams. What about something like calcium hydroxide, CaOH2? Now what that means is we've got 1 calcium. We've also got an OH in here, so oxygen and hydrogen. So there's a couple of ways you can do that. So I know that, for example, oxygen and hydrogen, so that'd be 16 plus 1 is 17. And then because we've bracketed it and put a 2, that means we have 2 of those. So you'll see down here with the calculation, 2 OH is 2 times 17. So 2 times 17 would be 34. And then calcium, and if you go to our periodic table, we'll see over here calcium, 40. So there's the 40. So 40 plus 2 times 17, 40 plus 34, and that is 74. So 1 mole of CaOH2 is 74. And finally, as a worked example, sulfuric acid, H2SO4. Now, H2SO4 has 2 hydrogens, S is sulfur, so 1 sulfur, and 4 oxygens. Now, I've seen all of those before. Hydrogen's 1, so multiply it by 2. Sulfur is 32, and oxygen is 16, so 4 times 16. So 2 times 1, 2, 32 times 1 is 32, 4, 16, 64. Add those together, and the mass is 98. So 1 mole of H2SO4 is 98. So to practice it, you'll see some examples on the page in your notes. So pause this video and work your way through those and do exactly the same thing. So look up the numbers in the periodic table, then add them together and see what you get. And in a moment or two, again, I'll go over the numerical answers. Now, I'll not get time to work out all of I'll not take time in the video to work out all of the answers. If there's some, whenever you see the answers, you're not sure where they came from, you can contact me by email or through Google Classroom, and I'll go over it with you and show you where those have gone wrong. Okay, so the figures, sodium chloride, so there's just the first one I've shown there. So sodium's 23, chlorine 35.5, so 58.5. The others, magnesium, well, there's sodium chloride again, 58.5. Magnesium bromide totals up 184. Aluminium chloride, 133.5. Lithium carbonate, 74. Zinc sulfate, 161. Ammonium phosphate, 149. Oxygen, now it's O2, so 16 is oxygen, we had to multiply it by 2, so 32 grams. Chlorine, 35.5 times 2, 71. This one, C2H6, 2 carbons and 6 hydrogens, 30 grams. AlOH3, 78 grams. Al2SO4 3 times. Now double check your maths if you haven't got the figure, and if you're still not getting that, email me or go through and see where that's gone wrong. So 342 for it. And sodium sulfate, Na2SO4 142. So hopefully you've been able to go through those and those work out the masses. Now what that means is that if you took all those substances there, and you weighed out the number of grams of each of them as shown, what you'd have in every single sample, in every single beaker or whatever you've put those into, you'll have exactly the same number of particles. You'll have 1 mole of NaCl, 1 mole of magnesium bromide, 1 mole of this one here, NH3, NH43, PO4, and so on. So that's the mass of 1 mole. Okay, so what we want then, quite often, rarely in chemistry will you use 1 mole, because it's a lot of number, it's a lot of particles, it's a big number of particles, a lot of them. So quite often what you're requiring is a fraction of that, so something like a quarter of a mole, 0.25 mole, or half a mole or something like that. Now, if you want to work that out, the first thing that we do is just that calculating routine. We work out the mass of 1 mole. So look at the formula, and we total up what the mass of 1 mole is. And then if it's a fraction, all you do is multiply the mass of 1 mole by that fraction. So, little equation, mass equals number of moles times the mass per mole, that RFM. So that can be shortened down to mass equals N times RFM. So, look at the first example. What's the mass of 0.25 mole of H2SO4? Now, on the previous page, we'd seen that H2SO4 weighed 98, so 1 mole is 98. 0.25 mole, therefore, is a quarter, 0.25, times 98. So if you multiply your fraction by the mass of 1 mole, you get the number of grams, and your answer here will be grams each time. Few worked examples to show you. So in each case, we work out the mass of 1 mole first. So for magnesium chloride, Mg 24, so you see the 24 there. Chlorine 35.5, so times it by 2, so 1 mole is 95. Half a mole of it, therefore, is going to be 0.5 times 95, 47.5 grams. 2 moles of bromine, so let's work out 1 mole of Br2 first of all, so Br is 80, so multiply that by 2. Then that gives you 160, so 1 mole is 160, and then 2 moles is going to be 2 times 160, 320 grams. Now, these ones over here, we haven't got a formula for these, so let's work out the formula first. So sodium nitrate. Now, if you're not sure of it, again, I'll flip up the periodic table just to remind you of this. So sodium is here, so remember group 1 is +1. If we go to our data sheet, nitrate is there, NO3 minus 1, so Na plus 1, NO3 minus 1, so the formula has to be NaNO3. So NaNO3. Then 1 mole is going to be 23 sodium plus N, 14. Oxygen, 16 multiplied by 3, so 1 mole totals 85. So 0.25 mole is then going to be 0.25 times 85, 21.25 grams. And then finally in this section, zinc hydroxide. So again, let's work out the formula. So zinc, if you go to our data sheet, you'll see down here, zinc is always +2. Hydroxide is over here, OH minus 1. So Zn plus 2, OH minus 1, Zn, and then 2 OHs. So you'll remember whenever we put that in place, the way we show that, Zn brackets around the OH, 2. So the mass of 1 mole, zinc is 65. So look at our periodic table. Go back here, there's the 65 for zinc. Hydroxide is an oxygen and a hydrogen, so 16 plus 1, 17. And then we're going to have to multiply that by 2. So 65 plus 17 times 2 gives us 99. So 500 mole, which is what we've been asked of this one, 500 times 99 for 49,500 grams. Or if you're doing that in an exam, it might ask you in kilograms, so divide by 1,000 and you'd end up with 49.5 kilograms. Okay, so there's some examples there again for you to try. So pause the video and work your way through them. Again, I'll show the answers now in a moment. If there's any that you're not sure of, again, you can email me and go through it. So the numerical answers: half a mole of copper, 32, quarter of a mole of zinc, 16.25, 1.5 mole of hydrogen atoms would be 1.5. So if you look at hydrogen atom as H, so 1.5 times 1.5. Oxygen molecules would be O2, so 1 mole of those would be 32, so 2 moles would be 64. Carbon dioxide, CO2, so 2.5 moles times 44 would be 110 grams. Calcium oxide works out to be 7 grams. Copper sulfates, so formula should be CuSO4, so check your formula first of all. And then 1 mole works out to be 160, so 2 is 320. Zinc hydroxide, we saw back in the previous page, was 99, so 2.5 times 99, 247.5. Aluminium hydroxide, now the formula for it will work out AlOH3, so work out the mass then times by 5, so 390. And 1.3 of copper nitrate, now copper 2 nitrate would be copper Cu, nitrate NO3, and we'll have to bracket that, multiply by 2, so the formula will be Cu bracket NO3 2, and 1.3 mole of it works out at 244.4. Okay, so the next bit is then turning that around a wee bit, and what we might be asked sometimes is, if you've got a mass of things, so for example, you go to the lab and you weigh out a certain amount of, say, sodium chloride, how much is in that? And what we're going to do is we're going to count it in moles. Now, we kind of rearrange that equation that we had before, and the number of moles is going to be the mass divided by the mass of 1 mole. So if you think of the logic of that, suppose you had, for example, the mass of 1 mole was 50 and you had 50 grams, well 50 over 50 would be 1 mole, and that would make sense. Or if you had 100 grams and the mass of 1 mole was 50, 100 over 50 would be 2. So to count the number of moles, you divide the mass that you've been given, now that must be in grams because 1 mole is always in grams, and divide it by the relative formula mass. And then it's usually shortened out of this. So this is an equation that we'll use an awful lot. N equals M over RFM. So 2 worked examples are given to you. So 1 gram of magnesium. You asked what's the number of moles in the following? So you're going to count in 1 gram of magnesium. So what's the number of moles in 1 gram of magnesium? Now, what you do is you first of all find out what 1 mole is. So again, go to our periodic table, and magnesium's over here, 24. So 1 mole's 24. So 1 divided by 24, and straight away there's your answer, 1/24 of a mole. Or if you put it into your calculator, that works out at 0.042. 98 grams of sulfuric acid. So again, get your formula, RFM, you need the formula for that. So H2SO4 for sulfuric acid. 1 mole works out to be 98. And then if you divide your 9.8 by 98, that simplifies down to 1 over 10, or 0.1. And again, at this stage here, 9.8 over 98, don't be afraid to use your calculator and put the figures into it. This one, aluminium hydroxide, 19.5 grams of aluminium hydroxide. So Al brackets OH3. Now the mass of 1 mole works out to be 27 plus 17 times 3, which is 78 grams. Then to work out the number of moles, divide the 19.5, what we were given there, by 78. That's the RFM we've just worked out. And 19.5 over 19.5 over 78 works out at 0.25 mole. Okay, and then on the next page, you'll see some examples. So again, pause the video, work your way through these, and check that you can do them. So the answers: 3.2 grams sulfur is 0.1 mole. 2 grams of calcium, 2 over 40, 0.05, or that would be 1/20th of a mole. 64 over, and then O2, so 2 times 16 is 32, so that'll work out at 2 moles. 2.2 of carbon dioxide, 2.2 over 44, and that'll work out again at 1/20th of a mole, 0.05. 1 gram of magnesium oxide, 1 over 40 MgO works out to be, so 0.025 moles. Below it, copper 2 oxide, 1 mole of it will work out to be 64 plus 16, 80, so 2 over 80, 0.025. Aluminium oxide, 100 over the relative formula mass of Al2O3, 0.98 moles. And copper 2 sulfate, that will total up to be 160 if I remember correctly, and then 4 over 160, 0.025 mole. Now, that finishes off the bit that we have there in terms of the working through. You'll see pages 10 and 11. So page 10 is marked as being key questions, and then page 11 are just some further examples given from past papers and so on. So what I'm asking you to do is to work your way through those, write them onto paper, take a photo of it, and then send it through to me, either on email or in Google Classroom. Or if you prefer, on Google Classroom I've given you slides which you can type into. You can take and get a text box and then type your answers into it and show your working out, particularly for some of the harder examples, and then I'll see how you've got on with those. And those would be with me by 4 o'clock on the 27th of April. Okay.